Welcome. My name is Rella Dinesh from CSITA section 22951A3323. My topic is the application of the compensation theorem in the proof of Thevenin's theorem and Norton's theorem. Code AEEC01. Now we see the agenda first. What is Thevenin's theorem? What is Norton's theorem? Application for Thevenin's theorem. Applications for Norton theorem. Proof of Thevenin's theorem. Proof of Norton's theorem. Now we see what is Thevenin's theorem. Any combination of batteries and resistance with two terminals can be replaced by single voltage source and a single series resistor, or the value of E is the open circuit voltage at the terminals and the value of R is divided by the current with the terminals with short circuit. Below this is given that circuit, whereas VAB is an open circuit. In Thevenin's theorem we must open it. Now we see the Thevenin's voltage. The Thevenin's voltage E used in Thevenin's theorem is an ideal voltage source equal to open circuit voltage at the terminals. In the example below, the resistance R2 does not affect this voltage and resistance R1 and R2 from a voltage divider giving. Here they shown E is equals to VI R3 by R1 plus R3. Here we see Thevenin's resistance. The Thevenin's resistance R is used in Thevenin's theorem is the resistance measured at terminals capital A, B with all voltage source replaced by short circuit and all current source replaced by open circuit. It can also be calculated by dividing the open circuit voltage by short circuit current at AB, but the previous method is usually preferred and gives, where here we can see R equals to R2 plus R1 parallel to R3. Here R2 plus R1 plus R1 R3 by R1 plus R2. This is a formula of parallels. Resistance is connected in parallel. Now we see what is Norton's theorem. Any collection of batteries and resistance with two terminals is electrically equivalent to ideal current source. I is a parallel with a single resistor R. I is a current. The value of R is the same as that in the Thevenin's equivalent. The current I can be found by dividing the open circuit voltage by R. Now we see the Norton's current. The value of I is a current, we know. For the current used in Norton's theorem is found by determining the open circuit voltage at terminals AB and divided it by Norton resistance R. Now we see the applications of Thevenin's theorem. Used to simplify complex circuits, to determine change in load voltage, to predict range of load voltage variation due to change in load resistance, to obtain Norton's equivalent circuit, to determine maximum power that can be transferred to a load from the network. Thevenin's theory is used in source modeling the resistance measurement using the Whitestone bridge. Now we see the application for Norton's theorem. To simplify the electric circuitry of complex, it is summarized into a current source where current constant IC and equivalent load Z equivalent, thus the computing voltage at the load. Norton theorem is usually to solve problem on parallel generator with unequal EMF and unequal impedance, widely used for circuit analysis, simplification and study circuits initial condition and steady state response. Equivalent current source and impedance in parallel. Now we see the proof of Thevenin's theorem. Consider the two connected networks shown in figure 2a here. Both the dividing network N1 and load network N2 are linear and may contain voltage and current source. We want to prove using the compensation theorem that as far as terminals property of N1 are connected, the system of fig 2, we can see in fig 2a, can be replaced by fig 2b. Fig 2 is fig 1. In fig 1a, N1 is replaced by Z. We can see in, we have saw in fig b. Okay, here Zs is impedance looking back into N1 with all source in N1 replaced by the equivalent impedance. Voltage 1 is the circuit voltage of N1 measured at terminal 1 by 1. Fig 2, Thevenin's equivalent of linear network. A is a original connection of two linear network. B, Thevenin's equivalent of N1. Now we see proof. Consider N1 and N2 connected as shown in figure 3a. Both networks may dependent voltage of current source as well as impedance source. Representative impedance, voltage and current source have been shown for each network. It is assumed that there is no coupling between the networks other than provided by connection made at terminals 1 by 1. It is further assumed that there is a positive current I into a terminals 1 for load network N2. Now introduce an impedance AZ in the line connecting N1 and N2 as shown in figure 3b. The addition of this impedance will cause a change AI. The current into a load network. It is assumed that this change will carry its own sign. In order to determine the magnitude of this change in current, the compensation theorem may now be employed. This results in a complete equivalent network representation shown in figure 3c. These figures are in next slide. I will show that after completing this. It should be recalled at this time that network of 3b and c are completely equivalent as far as calculations of IL is concurred. Moreover, consider the voltage VI across the impedance AZ in figure 3b. Here you can see Vg is equals to I of AZ plus AI of AZ. Here you can see that A is a two linear networks and B is added series impedance. C is a result of applications of compensation theorem. Note that the voltage across combined voltage source AZ and series impedance AZ in fig 3c is identical to V. Indeed, these two voltages will be identical no matter what the magnitude of AZ in fig 3c. A loop equation can be written around the loop formed by connection of the two networks in N1 and N2. This figure is a fourth equivalent network. Voltages will be identical no matter that magnitude delta Z in fig 3c. A loop equation can be written around the loop formed by connection of two networks N1 and N2. Here, I of delta Z equals to minus delta I Z1 plus Z2 plus delta Z. It is a second equation. Using second to eliminate I from 1 result in V Q equals to minus delta I Z1 plus Z2 it is a third equation. Now observe that fig 3b. Observe that fig 3b here. Observe this fig 3b whereas voltage in current Vm2 and In2 is upward direction. Okay. Now see. Now see that now observe from fig 3b that a limit delta z extended to infinity, whereas Vq equals to V base 1 minus V base 2. Okay, now we see whereas V1 open current voltage of N1 and V2 open circuit voltage of N2. The magnitude of V1 and V2 will always finite unless networks N1 and N2 are composed of series ideal current source. In this case, the limit of 4 will be indeterminate. This special case can be treated by limiting process from fig 3b as we seen in previous slide. Limit delta z extend to infinity, delta I is equals to minus I, since the total current must be 0 under open circuit condition. Therefore, from third equation, limit delta z extended to infinity, Vq, you can observe that it is a Vq, limit delta z extended to infinity, whereas minus delta I into z1 plus z2 equals to I z1 plus z2. Equation 4 and 6 result in Vi equals to V1 equals to I z1 plus z2 plus V2 with an associated equivalent circuit as shown in fig 4. Now V1 and V2 depends only upon elements in N2, that is change sorry, in N1 in no ways affect the indicates N2 network. This is a direct result of assumption of no coupling between the networks. Thus, as so far Thevenin's condition are concurred, N1 and N2 equivalent and N2 equivalent, since the Thevenin's theorem is proved. Okay. We prove that Norton's theorem. Norton's theorem can be derived from Thevenin's theorem simply by making voltage to current source transformation. In the equivalent network fig 4, we may conclude therefore that Norton's theorem is also a special case of the compensation theorem for linear network. The proof of Norton's theorem begins with placement of an impedance Az across terminals 1 by 1 in fig 3a. In fig 3a, the dual of the previous state's compensation theorem is then required to calculate the change in terminals voltage. This added impedance produces the proof of straightforward and follows directed from limiting argument as Az is allowed to approach 0. Okay, here we see all the proofs of Thevenin's and Norton's from compensation theorem. Okay, thank you. Have a nice day.